All right, everyone, we'll get started here. Thanks for coming here today. We'll have two presenters, which will be introduced by Andrea, and one of our other presenters is online. So I'll invite Andrea to come up on stage and invite the presenters.
All right, why are we all here when it's such a nice day? Because we love landslides, we love dirt, and we like being entertained by the likes of Andrew and his shirt. That was unintentional, Andrew. So I'm here to introduce Andrew, Marten, and Brian. So this is on the Chilcotin River landslide. So last year on July 30th, at about midnight, up in the Chilcotin region, there was a 7 million cubic meters landslide that went and cut off the Chilcotin River, and then over the subsequent days it then started to breach. They will tell you more about it, so I will stop. It was all over the news and highly watched. And I know at my parents' farm it was definitely muddier in the Fraser River afterwards. So Andrew, he's got his doctorate, makes me feel super dumb about particularly landslides. He's our BGC's Geohazard Knowledge Center lead, and so I get to work with him on a regular basis from that perspective. He enjoys on-the-ground geohazards assessments. He just got back from Dominica, and he will be off to sightsee in a couple days, so it was really good that he could slot us in for this. I like to always throw out a fun fact about people. His fun fact is he likes to turn technical topics into haikus. So you can quiz him on that afterwards and see if you can come up with one on the spot. I know I had ones developed for different critical states with haikus, and we had a whole competition. I cannot remember what the winning one was. So Marten is our next one. He's a research geomorphologist at the Ministry of Forests. He's sitting, wave your hand, out in the middle of the row there. He has an expertise on landslide mapping, geohazards. He has a Ph.D. as well. So again, I am going to feel really dumb today. And he's currently at, you got your Ph.D. at the University or Northern, sorry, I'm going to stop. Anyways, I'm going to stop on that one and just go to his fun fact. He, as a kid, was forced to wear knickerbockers with green stockings and understands that he has some childhood trauma from that, which we all do. The last one is Brian. I didn't get a fun fact from him, so unfortunately you don't get to be entertained by that, but maybe Brian can give you one himself. Brian is a professor at the University of Northern British Columbia, and he's currently on a 2-year exchange working with the GSC, and he's also the chief scientist at Sockeye Institute of Airborne Coastal Observatory. So, Andrew, I think you're up first.
Thank you, Andrea, and don't worry, it's mostly pictures, so everyone should be able to have fun.
Much appreciated.
So, yeah, just a brief run through. Since you've now been introduced to all of us, I'll be kind of setting things up with the Chilcotin River landslide and walking through the progression of the breach of the landslide dam. And then I'll turn it over to Marten to talk a bit about the landslide history, some commentary on that, and then looking at post-breach. And then Brian is going to walk us through some Lidar analysis he's done for the valley following this event. So, and then at the end we'll open it up for some Q&A. So getting right into the Chilcotin River landslide emergency response, this being from the geotechnical perspective. There were a lot of folks involved in this, a lot of different government agencies, different people with different interests, but that's going to be the focus here. Just to situate ourselves with where we are down in, I probably should have slid the star a little bit more over into Burnaby, but we're approximately there, and where this occurred is 300 kilometers almost straight north, but if you try to get there, you can't get there in a straight line. It's a very circuitous route. So we have the Chilcotin River flowing into the Fraser River, and the landslide occurred just upstream of one of the large creeks that feeds into there that's creatively called Big Creek. And this photo down on the bottom corner there is kind of the first photo that came out, and it's kind of small and it's kind of hard to see. And that was kind of the nature of the initial information that came out. Like, there was something happened and it definitely blocked the river, but what exactly is going on there? So a little bit more on where exactly we are, because this is in quite a remote area. So a lot of the focus is really around what's happening with the rivers here. The political boundaries, the roadways are nearly as impactful as what the water is doing. So the big colorful area is the Fraser River watershed, which drains a whole lot of this province all down towards where we are now. And so the Chilcotin is one of the major tributaries in what's known as the Middle Fraser. And why this is of concern is this is a major spawning run for Sockeye and Chinook salmon. Sockeye salmon particularly spawn in lakes. Some of their two main remaining spawning grounds are up by Quesnel Lake, which is right by where the Mount Poly tailings dam failure happened, and in Chilco Lake at the headwaters of this. So, with that, these two lakes are kind of incredibly important for that's ecological standpoint. As well, this area is within the traditional territory of the Chilcotin Nation and the Sequamip people. So they have a lot of important sites for their kind of fishing usage, cultural heritage, all that very important area for both those people. So when we look at what happened, as alluded to in the intro, we had about 6 to 7 million cubic meters that came down. We're able to quite rapidly get a rough estimate of that volume from those initial helicopter surveys, doing some photos, building photogrammetry models, things of that nature. The blockage was about 700 meters along the valley and around 50 meters thick. A little bit upstream of here at Hansville, there's a Water Survey Canada gauge, which was able to show us that there was consistently about 200 cubic meters every second adding into this lake. So definitely at the time when this photo was taken, 2 days after, or day and a half after the initial slide occurred, there's definitely that water level ticking up was definitely on everyone's mind. So being that if I just go back for a moment, looking at this very first helicopter flyover, that looks like a pile of dirt, not a pile of rocks. So being that we're in interior BC, natural question goes to what did the glaciers do? What's the material that we're dealing with here? So looking on the left-hand side there, all of the arrows are flow directions for the glaciers coming down. So you can see it's kind of starting from the southwest and moving to the northeast. The Fraser River is wanting to go from the north to the south. So that's telling us we're getting blocked drainage paths, the speckled area in the middle. Basically all of our paleo valleys now getting infilled with glacial lakes, glacial lacustrine sediments, which I'm sure a lot of folks in here have had fun times dealing with in various locations across the province. And so this is a section from a paper by Isles and Clegg from 1991, and don't worry about the details. There's a lot of things going on, contacts, different interbedded things. It's a very complex sequence, so just from a very quick bit of Googling after the event happened, we were able to know that we should be expecting a potentially quite complex glacial sequence that we're going to be dealing with out on the ground here. Another thing that came up very quickly as we were looking into this event, and something that Marten's going to talk about in quite a bit more detail, is there's been a history of landslide dams in this area. So for about 7 days in 1964 at Farwell Canyon, which is about 10 kilometers downstream of our 2024 event, the river was dammed. There's a photo of it. There was also a reactivation of that same slide in 2004, which blocked the river for part of a day. And in both cases, the reports were that those dams were eventually overtopped and progressively eroded their way through. So with this context, we'll start turning on the hazard and risk scenarios that we need to be considering as we're dealing with this event. So when the dam breaches, there is the downstream effects of that's going to release over however long the breach occurs. All those 200 cubic meters every second is going to come out a lot faster than that. So flooding, erosion, debris impacts downstream. And really how fast that breach occurs is going to dictate how bad the downstream effects are. The immediate thing that was realized was the blockage of fish passage. This happened pretty much right about exactly when the salmon run was supposed to be starting. And then the other big hazard scenario was we now have a lake in these glacial lacustrine sediments. So we're saturating that, and then we're going to rapidly draw it down. Also not good for slope stability. So the question of what will happen next, and by the way, the from my perspective, the folks we're working for were looking for a preliminary assessment the day after this photo was taken. So needless to say, this is not going to be something that's agonized over, not a lot of time for second guessing. So the initial task was an initial assessment of the dam stability. Not going to do any boreholes. We're not running any flak analysis. This is being done on Excel. But the big question is, what are our failure modes? And just like a constructed dam, this can go over by overtopping or piping. So for the piping particularly, this isn't a nice constructed core, filters, zone construction. Nature's QA/QC program is pretty loose, but the production rate of this was excellent. So given the very limited information, trying to figure out what the likely failure mode is. So given that we're 700 meters long, 50 meters thick, that's a pretty low gradient, so we'd definitely be much more concerned with piping if it was kind of skinnier and taller, get a much higher gradient going through. Another thing, just standing at the toe and looking at it and looking very closely, trying to find any spots where seepage is coming out, and really couldn't find any evidence of it. And there were regular drone flights going over, collecting imagery, allowing to continue to check for any zones of seepage developing, which wasn't happening, which was good assurance that we were probably trending towards an overtopping failure, consistent with what happened in 1964 and 2004. So getting a bit deeper into this, given limited time that we're doing all of our analysis in Excel, what can our empirical analyses tell us, considering that the faster that dam fails, the greater the peak discharge is, the greater the downstream hazard. So basically at this point, we roughly know how big the failure is, and we know where the failure is, which is somewhat trivial, but we've got, through our Cambio system, we've got the river network tools, which gives us the whole North American stream segments, everything. So can quickly get what the upstream catchment area is and what the slope of the river is. So those are a rough proxy of the river power, so how much capacity it has to move sediment. And then when you have the volume of the event, your sediment, capacity to move sediment, there are some handy tools that can be quickly calculated to give, found that this is definitely in an instability domain, so we don't expect this to form a long-term stable blockage where we'd have a big step in the river. It's going away. There is more than enough river capacity to move what we've put in here. And then the other big question was, how long will the breach take? So again, firing up our nice spreadsheet that somebody had developed for us, we're able to get plugging in some numbers, getting breach durations in the range of 6 to 8 hours. One of the big inputs is the lake volume, which at this time we had a huge amount of uncertainty on because there had been Lidar flown, but it wasn't processed for the upstream area, so it was a very thumbsuck what that lake volume was. And then there's also this sticky question of how confident are we in the analysis, because looking through what's the data that was used to fit these empirical relationships, it's not that great of an analog to the case that we're actually looking at. So taking that with a grain of salt, and knowing that we did have 2 examples from the area that breached in the course of kind of hours to days, made us think that this is probably a bit to the lower end. We're likely in kind of a 6 to 24 hour breach duration seemed reasonable. That's what we said the day after. So let's see what happens when prediction meets reality. On the August long weekend, I did not originally plan to go to Williams Lake, but there I was. 4 p.m. You can see just off here we're awful close to the top, and there was quite a bit of concern that the thing would overtop in the middle of the night, which would have made the kind of initial response much more difficult. And also, there's a bunch of people who really wanted to nerd out on seeing what happened when this thing breached. So quite a bit of anticipation going to bed that night. But as we get to Monday morning, about 7 in the morning, it first started going. This is at about 9:30. It was really starting to come through then. So we have a breach developing. The worst case scenario that was considered, KWL did the hydrotech part of it, and they had done a worst case breach of a 1 hour breach duration. At this point, we're already about 2 hours after the very first start of the breach. So at that point, we're confident it was not the worst case 1 hour breach scenario. That was good. But then the question still remained of how is the rest of it going to go? So if we jump ahead to about 1:30 in the afternoon, now the breach is really rocking. The after the fact estimate is that this is about 4,000 cubic meters a second coming through there. Very nice hydraulic jump in the bottom there. Like that's and you can really see immediately downstream how the natural banks are just getting blown out by this amount of flow coming through here. And then chasing down to where the Chilcotin meets the Fraser, right about 2 p.m. was where that first raft of debris made it down there. And you can see just a huge amount of woody debris that's being carried by this. And then getting to about 8:30 p.m. golden hour light, we can see that there's still more than kind of the base flow of the river coming through there, but the flow is really starting to ease down. We're well past the peak of the flood, and we're kind of into a slower, steadier draining of what's left of the lake at this point. Some other interesting points. You can see this darker gray material that's down on the bottom, just flying by there. The progression of the breach was really influenced by this till layer that was higher up in the sequence that got all down. So there was a lot of the material was kind of fine sand, silty, very rapidly erodible, but then it hit this more cohesive, massive till unit, and it really created a bit of a step that helped control the rate of that breach progression. And then finally, moving ahead to Tuesday, day after the breach, you can see here all that wood and mud coming down through the Fraser. A bit of a, usually this is at the confluence of the Thompson and the Fraser River. Usually the Thompson is dirtier than the Fraser, but that was definitely switched this day. Yeah, kind of by the end of the day on the 6th, it got as far as Hope. By the 7th, it would have been by your parents' place. And really, as this occurred, this really was about the best case scenario that we could have hoped for. It was a very steady breach progression. Definitely a lot of impacts in the Chilcotin Valley directly up to the Fraser confluence. But once it reached the Fraser, basically the water level didn't come up any higher than your typical seasonal flood. So the effects there were relatively limited. And yeah, after that brief run through what happened, maybe turn it over to Marten for some of our history lesson.
So first I'm going to talk a little bit about the historic landslides. So here you see the same vantage point for this is about 1.5 kilometers below the Farwell Canyon Bridge, 1964, and the same source area evacuated in 2004. These are, one thing to note, all of these 3 landslides happened during low flow conditions, kind of in the late summer, August, September. Now, these landslides are translational landslides, all 3 of them as well, meaning they kind of move as a rigid block and there's not too much rotation, so they break up as they travel. Here's another view of the 64 deposit, and this is the 2004. Is there a mouse, or do we just use our fingers? Does that work? No. Anyway, that doesn't.
There's like a pointer on the.
Yeah. What?
It worked.
Oh, like this worked?
Yeah.
Oh, I can't see where it's working. Oh, there. So this is all a really hummocky deposit, which was kind of a fluvial terrace before, and yeah. So, and the 2004 landslide obviously didn't climb up onto that surface, but was built up against it. It's quite a thick deposit, so you can see the fluvial sediments below the dashed line there, and the 64 surface above that. So, and this is the same view of 2 areas. So you can see, again, this is kind of a fan terrace over there with the white arrow for 64, and then that hummocky surface coming up. And you can also see that the deposit, that it changed the position of the river. There are fairly old trees growing on the pre-64 surface. You can see that here, like all through here. They would be Douglas firs mostly, and they haven't come back. But we also did an ecological study where we looked at a site downstream and kind of tried to reconstruct what that forest would have been like on that site. This is the lake above the dam in 2004. So you can see the bit with the trees in the background from 1964, and then this is 2004. And that lake then was sort of in the 18 to 20 meter high range. Downstream, a dry riverbed. And you can see where, I think this was the Fraser River at Hope, maybe. You could see, you could trace this from Hope, and I think the other one was at Texas Creek. Actually, don't know which one that is, but you can see the drop in the flow of the Fraser, and then the flood peak when the dam broke. And this shows that the impoundment went some distance above the Farwell Bridge. You notice that this is not concrete. The new bridge has concrete, what do you call those side things on the bridges? Yeah. The other bridge burnt down recently. And this was pretty cool too, kind of a geomorphic impact. You can see where all those small gullies are truncated by the 2004 flood level. So it's interesting to look for little clues like this in the landscape. Unfortunately, this didn't last for 20 years. So I looked for it and I couldn't see it back anymore. So it's been modified already. What was interesting is that we were able to find the rupture surface of the 2004 landslide, and I think that's about 25-ish meters above river level. And there it is again. So it's a very thick, very dense unit that has strong slicken sides on it. So the material below is glacial lake sediment, and the above is probably 1964 colluvium. And then we peeked around a little bit in the valley, and we were looking for evidence of older landslides. And Brian will show us some on the Lidar later. But this was just upstream of the 64 slide. And we have found this type of situation in other river valleys in BC, where within the landslide dam body, in the lake, you would get a rapid accumulation of sediment. And that would preserve, these are rooted trees, and they're still in the vertical position. And they would be surrounded or buried in sands usually, or silts, and then they would be preserved. And so this one is sort of an event that was 600 or 700 years old. And I saw other evidence of this on the river as well. Upstream of the bridge, but when I wanted to sample it this year, the river had already removed it, so that was unfortunate. Tim Giles here, who lives in Kamloops. This is in the main scarp of the 64 and 2004 slide, and what we see here is a little bit of the history of the valley. Those big glacial lacustrine rip-ups in the sand matrix tell us that there was a very violent ancient flood there, and so there were shows a little bit of the history of the valley. Let's talk about the dam break cascade and some of its consequences. First of all, this is from artist and geomorphologist Dave Huntley, who is in the audience with us. He likes to paint most of his field sites. Very nice. And that's distracted me from what I wanted to say here. But yeah, so this is the landslide again. We it moved very much in a translational format. There's a large body of material here that was a little bit disturbed, but a lot of the trees were still in the growth position. Now there was a person camping here when the landslide happened, and I don't know exactly what happened, but he ended up breaking his leg, didn't he? And he lost his dog. He was on this side of the river. He had a raft with him, an inflatable raft. And I don't know if he got tossed up in the wave or what happened, but he was stranded on this side of the river. And there's a ranch just up here. You can see the irrigated fields there. And the rancher heard him at some point. And so anyways, he got rescued.
And the dog was found too.
The dog was found weeks later, right? Yeah.
Like a week later, yeah.
Yeah. So yeah, translational slide. And interestingly, too, on this slide, is it continued to deform in the week following the slide, but also afterwards. And so it'd be really interesting to have a close look at the Lidar from the different stages, because the material, like we camped here, you could see some trucks. So we were here around the clock watching it for about a week. And you could see the mass break up to some degree. I got a little thermal camera, a little thing that you could stick in your iPhone. And we heard a big bang at about, when was it, 3 in the morning? And so I got up and there was a reactivation. So, and obviously that was colder than the other surface. So that was interesting. And then the overtopping began at 7:07 a.m. on August 5th. And we were worried that it was going to happen in the middle of the night when we couldn't see it happen, but this was nice. And here's a little. Oh, how do I play this thing now? Like a, what? Oh, I don't. Oh, I have to go here. Oh, here. Sorry. So this is showing material outside of the dam. So the valley walls break up. But it also, the camera pans out a bit, you can see that the dam itself is reaching to, you can see the flat part up above and then the steeper part where the dam is. And the gentler slope of the water outside. So there's a tremendous amount of valley wall added to this sediment budget of the river. It's not just the dam itself, it's walls of the valley. How do I get out of that? Oh, maybe this way. Oh yeah, and this is also quite cool. This is just downstream of the dam, and it's beautiful anti-winds crescent shape. They tended to form just downstream of where we had a lot of sediment bank failures. If we had a bank failure, these things tended to form as well. And there's also where all those trees are standing up, those are little dunes forming around those as well. And before I thought we could only find evidence of buried trees in the lake up above the landslide dams, but here a lot of these trees were being buried as well. So they could provide some geomorphic evidence down the road as well. Things below dams as well above dams. Let's keep going. So then we went, I did about 5 flights, I think, around that time with a helicopter. And so one of the reasons for doing a flight was just to advise the regional district about the evacuation status of the evacuation order, and with knowing that BGC and KWL were going to do more detailed analysis, but this was one of these rapid reconnaissance things. And then, so we noticed that post drawdown, as expected, there was a lot of movement. We had some temporary damming here, but probably an hour rather than a longer time frame. This too is above the dam. I was there in mid-March, and you can really see that there's a lot of instability in these valley terraces, and a lot of lake sediment in that material, glacial lake sediment. So one of the things that concerned me as soon as I learned about the landslide was that I had seen in this kind of orange area where it says rock slide that there was an old rock slide there. And what happened with the July event, which is in red, that landslide, it removed the toe of that older landslide, or part of the toe. So we're having a really close look at that thing to make sure it doesn't reactivate, because it's got quite a large volume and it's also higher on the slope. And there's bedrock involved in that too. And when you get a bedrock landslide, those dams tend to persist far longer. And then the yellow material is that glacial lake sediment, or that lower valley fill, which is very unstable. But because it's a smaller volume and it's lower in the valley floor, if it does close the valley, it probably would be fairly insignificant compared to the larger events. We had a reactivation on the 16th of September, and again a few days later, and that came actually from the opposite side of the valley. So you can see that initially the movement was from here, in this direction, but now it came from that way. And that produced a dam, I think it was about 7 meters high, but it didn't last very long. And when you look at, I don't have a copy of the hydrographs here, but when you look at the main hydrograph and then these ones, they're like this and this. Here we can see the position of those dams on the Lidar, and that's obviously the background is a photo of the dam before it failed. Also, effects of the downstream flood. It reactivated this dormant landslide, which is some 2.5 kilometers below the dam. But more importantly, here near the yellow line is the Forest Service Road and the Farwell Canyon Bridge. The green polygon is a 64 and 2004 slide. The red stuff, and this is, Brian will show similar things like that, is erosion from the landslide. And so there are two things that are really important here, or of major concern. One is this purple polygon here. So that right there, this is an incipient bedrock slide that its toe was eroded by the flood, and the slope responded. It partially failed. And then the other thing we're worried about is the green polygon, obviously, because that also underwent a fair bit of toe erosion. And that could play a role in destabilizing that mass as well. And I think Brian may have some recent photos, because we just had a Lidar flight flown on the 31st of March. Oh yeah, this is another small animation. This is planet imagery. So it just will cycle through, and I might have to play it again. But one place to look is right here at this location. And can I play that? You just keep looking up there, sorry. So you can see that was a really important, that was called Pothole Ranch. And the flood removed about 6 acres of land there, and about 2.5 hectares. And was totally removed that. And that was a really important archaeological area. So it's really unfortunate for the First Nations. And then you can see changes down below as well, but I won't play this again. So here's an example of some of the bank erosion that happened at the 2004 64 landslide. You can see it right here, especially right there. Pretty aggressive erosion. I think maybe up to 20 meters into the bank. That's the same view in mid-March. And then further downstream as well, we see severe undercutting and oversteepening of banks. And so one of the things, this is far away from any infrastructure, but even people like rafters and jet boaters on the river would be cautioned about these types of locations. And this is part of where the Pothole Ranch was. So the material here, there used to be the terrace below that. That was part of the kind of heavily used by the First Nations. And again here, looking upriver. So that's all recently been eroded very severely. These are the cracks that are in the bedrock. And prior to the flood, prior to the dam break, they didn't exist at all. And a fair bit of that material has been removed. It was probably a lot of rubbly colluvium, I think, but fairly large blocks. And BGC is looking at that more closely. So next we'll go and dive into the Lidar change detection a bit more with Brian Menounos, who is online.
Thanks, Martin. I can't see anyone, so someone will have to yell to let me know that you can hear me. Can people hear me?
Yeah, just bringing up.
Great.
Just trying to figure out which way. There we go.
Yeah, if you just click the presentation, it should be fine.
Okay, I requested control. Let's see if it works.
Brian, you can take over.
Let's see if I can. Nope, it's still sort of frozen for me. I keep hitting the button, but the request is not accepted. So what I could do is I could just ask you to advance my slides.
Brian, I think you're muted.
Nope. Can you hear me? Hello? Can anyone hear me?
I think you're still muted on your end, Brian.
Nope, not muted.
Okay, try now.
Hello? Can you hear me now?
Yes.
Okay. The request control, let's see if this is going to work now. Oh, there we go.
Yeah.
Okay, great. Okay, let's get this started. So thank you very much for the invitation. So I'm speaking from Prince George on the traditional territory of the Lheidli-T'enneh. I'd like to call out Adam Hawkins, a former student of mine, so I put him on the slide here. He actually reached out to myself and Marten. He was working for EMCR, Emergency Management Climate Readiness, BC. And so when this particular thing happened, he reached out to us to see if we could at least have a quick overview with him. And that's really how it started. I forgot to tell you a fun fact. I've always wanted to do karaoke Copacabana. And if I was there, maybe I would do that for you, but you're just gonna have to wait until the next time. Second fun fact is I think I learned more about fluvial geomorphology standing on the edge of this incising landslide than I think I knew prior to that point. Andrew talked about these diamictons. Diamictons really did save the day. And you could see as that flood was incising into the material, it was actually causing incision, but also backward propagation of these nick points. It was truly, truly phenomenal. So partly because of my work with the Sockeye Institute as a research associate, we were quite interested in this event once it happened. We reached out to the province and got a hold of the BC-wide mapping Lidar that was collected in May of that year. So we had a pre-slide surface from May 24th, and then we subsequently started to collect Lidar. And as Marten said, in 31st of March of this year, Terra Remote Sensing did a helicopter-based Lidar. So all of the Lidar data sets were co-registered, just trying to minimize errors for slope and aspect using algorithms that typically the sort of thing I do with glaciers, that's a common thing that we do. And then we remove the biases from those. The uncertainties on the Lidar is on the order of about plus or minus 20 centimeters. So certainly good enough for what we were choosing to do here. I'm going to skip that because we're kind of running out of time. But I will say that we have an aircraft that we use for trying to understand mass change for glaciers, but also just general topographic change in the province. And last summer, we had upgraded our LiDAR system to a Regal 1560. So this is quite a new system for us. And so it really provided that opportunity to test and see how well it actually performed relative to a earlier LiDAR system that we had. So Andrew had mentioned the glacial history of this landscape, and Dave is there. I understood, I wasn't sure if he was going to be there, but certainly pick Dave's brain, because this is an area of which Dave was doing his Ph.D., this broad region. What you can see from the LiDAR is if you look carefully, you can see stream sediments here. These are ice flow drumlinized terrain. And if you look carefully, you can also actually see that in some of these large amphitheaters, there's also material that has been streamed and deformed by overriding ice. So part of the story here is that it is a complex history of the interaction of ice on the landscape and subsequent instability, and also fluvial erosion and incision and deposition. I won't get into the details here, but here too, Dave, you're saving me time in my presentation. This is a open file report that Dave is working on. He's sort of mapped out the superficial geology, the cross section, and what I wanted to point here is this cross section that Dave has produced, showing the topography and where that slide surface was, and with respect to the valley geometry itself. So this is LiDAR that was, it's a hillshade image taken from the LiDAR in May 20 prior. So this is the pre-slide event, but immediately you can see that this is a landscape which is riddled with former evidence of former instability here. I want you to keep your eye on this slope here as I move back and forth between the pre-event LiDAR and also the post. So that's the particular landslide that we're talking about that dammed the river. But you can actually see that during that failure, you actually had lateral instability being moved by that slide itself. And so when you actually do a volumetric assessment using the LiDAR, I get on the order of about 7.6 million cubic meters. So pretty close to what Andrew had obtained from the from the helicopter imagery. What we also were doing in the field, so Adam, myself, and Marten were there on the shores for several days. We had some time and we had the pre-event LiDAR. We were quickly trying to fill up, because we had this pre-event LiDAR, we could actually start to fill up the corresponding water. We were just flooding the landscape and kind of found that we were estimating about 577.5 meters. This more or less was the area at which the overtopping occurred. And as I mentioned, and you've heard throughout this evening, standing on the shores here, you could just watch this backwards migration of these incisions, really by these competent diamictons, which really slowed the rate of incision throughout the landslide itself. Okay, I'm going to give you a couple examples of some of the elevation and channel change that we see here. So this is an elevation change map between two surveys from the 8th of August to the 4th of August. So they've been co-registered and differenced. You can see that over that period of change, the landslide has now been breached. So what was formerly high water has now been removed. So that's why it's shown as a negative. And as we zoom in, I'll sort of walk down the channel here on these 4 examples. So this first one, Marten had, let's go back. Marten had referred to this lateral incision. So you can see this here. There's also, between these two, the 4th and the 8th, there was some channel aggradation as well. This is this landslide that Marten had shown you an example towards the end of his presentation. You can see that there's some instability, some movement, and then also the bulging toe here. This is a little bit closer to Farwell Canyon. So this is the area that Marten concluded with, this rock slope. And you can also see evidence of former landslides. This was an earlier event. And there's a general pattern of aggradation and degradation. What's difficult, and you can see this throughout the individual surveys, is that largely due to the uncertainty of where the water was, it's difficult to come up with a cut and fill for the entire reach. That's going to take some time and some careful digitizing. This is the 1964 slide that Marten was talking about. You can see a little bit of deposition here, but you can see by and large this lateral erosion here along the margins of the Chilcotin River. In addition to this 64, you don't have the elevation in terms of contours, but this is a higher surface. And so we think this might be a much older event, not entirely certain where that's sourced from. Final piece, and then I'll conclude with a couple slides that show the elevation change from this last LIDAR survey. This is getting towards the mouth of the Fraser, where the Chilcotin and the Fraser come together. And so this is about 2 kilometers up from the Fraser River. You can see this in lateral erosion on the sides of the river. But what's notable here are these linear features. There's a step here, and there's also these linear features here, which indicate that there's been some movement, or at least I'm interpreting it to be some sort of movement. I don't think it's active right now, but certainly you can imagine that if this hillside went away or went down suddenly, you would create a damming event, which would be very, very difficult for the river to incise, largely because this is competent bedrock at this section of the river. Okay, I'll just conclude with a couple more images showing this elevation change. This is the landslide area that we started with. So this is the difference between our last survey last year and the 31st of March. This is the Terra remote sensing. You don't see a lot of change, at least on the former slide surface. You do see this reverse slide that Marten talked about, so that where the material had flown to the south or to the bottom of the slide. And you can also see some general channel change. But what's kind of cool is this is a farmer's field. So we drove past this. This had alfalfa on it in August. And I suspect because it's showing this net lowering, they've actually harvested it. So it's pretty cool when you can actually see these details in the LIDAR. So it gives us a good indication of the reliability of the vertical, the low uncertainties, and no real bias in terms of the elevation. I'll just show you just those 2 last examples here. So this is that large 64 slide in this former surface. That's the 20, and I'll just flip between. Doesn't seem like there's a lot of change there except the channel. And lo and behold, you see some lowering in the channel itself. Again, this is partly due to the water level, and you can see some very minor features, both cut and fill, associated with that. And then finally, here is this is the rock slope that Marten had concluded with. This is what it looked like in August, and this is what it's looking like in March. So not a lot of difference. There might be some extension of some of the upper cracks here, but not tremendous movement over that time period. And with that, I will conclude and turn it over to, actually I lied. I've got one more slide. So how much material was actually eroded by the river as a result of this slide? As I mentioned, it's hard to actually use the deposition in many of these areas, at least for the August 8th and the August 18th LIDAR, simply because there's some elevation change along the river water level. But what is apparent is that, by and large, the areas of net removal are really these areas along the river. And so if you took the net erosion downstream of the dam, we're calculating something on the order of about 5.5 to 6 million cubic meters of material that was mobilized from the the margins of the channel. So that's quite a substantial amount of material when you think that the slide itself was on the order of about 7.5 million cubic meters. And I think that is my last slide, so thank you.
All right, thank you there, Andrew, Martin, and Brian. Is there any questions for our three excellent speakers today? Yes, Isaiah.
Andrew, there were large woody debris from the photographs. How big are they? And is there any damage to any bush populations downstream?
Yeah. I guess I'll come here so it can be on the recording. Yeah, so the question was about the large woody debris mobilized in the flood and damage to downstream infrastructure. So this area, its interior is fairly dry. It's not like the very large coastal trees we have here, but this was, moving full-size trees downstream, and damage to infrastructure was definitely a concern coming into this. After it failed, one of the first places we checked was at the Farwell Bridge to make sure those abutments were okay. As Brian mentioned, the old one had burned down, so they built a new one, which was fortunately higher. And the flood kind of passed nicely through there without any significant damage. And then, as I mentioned, downstream, once it got into that's really the only bridge on the Chilcotin downstream. And then once it was on the Fraser, it was kind of beneath typical high water levels. So yeah, the wood kind of went nicely down until a bunch of it got caught in the big wood debris trap by Hope, and then the rest of it ended up in the Pacific.
P.J.
Do we know do you know which mechanisms contributed to the landslide formation? Maybe a very geotech question.
Yeah, no, well, it's a good question that I don't think we don't really know. There's a lot of things going on. Like Martin, you mentioned the time of year that it was lower flows. So in these three cases that were mentioned, kind of late July, early August, that's when the freshet has passed through. So river levels were higher, maybe get some more erosion. You've raised pore pressures in the bank. It drops down, so it's easier for things to mobilize. This site, there was quite a large wildfire in the area in 2017, I believe. That's one of those things where the link between wildfire and shallow landslides is very well made. The link between wildfire and deep-seated landslides is something where, honestly, I think we need quite a bit more research to look into that. So it could be a coincidence, but there could also be something there that, just don't fully understand.
There may have been some piping.
Yeah.
Go ahead.
Yeah, sort of building on the same question, I was going to go with the fact that there was a past wildfire, and look at the geology. I think I saw one of maybe it was Brian or Martin's limestone at depth, and then lava on top, and whether or not limestone might have a play in there, and then the piping issues as well.
Yeah, like the piping, there's you definitely have the much younger basalt cap on top of the limestones below can definitely lead to some hydrogeologic weirdness in there. Dave, do you want to say something?
Yeah, you do actually see there's actually a permanent spring above the headscarp. So I think there was clearly it was persistent water sort of going down the slope. In addition to the wildfire, though, back in 2012, the area was sort of quite heavily impacted by the beetle kill as well. So the slope has not supported a substantial forest cover for a good decade prior to the event.
Yeah. So even for one of these deep-seated things where there's some lag time between precipitation in there, but there's a long time. Yeah.
One of the revealing things, I think, when you on the exposed slide surface for about a week after, probably sort of persisting, you could see spring water rising out from the slopes. So clearly, I think that there was some caustic contribution at depth.
And I don't think it was an unusual like rain for like 10 days. I think it was a little bit of rain, but it wasn't unusual.
Yeah, nothing real precipitation-wise. But yeah, there was a lot of water coming out of that headscarp. Yeah.
You see that in some of the other glacial lake landslides too, like Big Slide at Grinnell. It's got all sorts of water coming out in lenses. That one seems to be connected to 10 Mile Lake, which is above it. But we've had a few other landslides too, where one in particular up in the Peaks, where the water coming out of the landslide was about twice the discharge of the water coming from the stream above. And that was just all in sediment. It wasn't traveling at a bedrock contract.
PGC Marten.
Oh, thanks, Aaron. I was almost forgot my question. No, Brian showed a Lidar image where you see tension cracks off to the east side. And then when the main failure happens, a chunk of that's still there. Is it possible that the slide didn't happen all in one go? It just took off a chunk of that east side and then that unloaded the tow and let the rest of it go? Or have you thought about that?
Yeah, that level of detail, not particularly. Like, and another thing with the some of the images that Brian was showing, you could see the toe of that was really like there was a lot more. There was precursory deformation everywhere, but there was a lot more right at the toe. So
but
yeah,
it seemed to be concentrated towards the east side.
yeah, on the downstream side of it for sure. Yeah.
Martin, you mentioned a rock slide just next to the landslide that eroded a bit of the toe.
Yeah.
Have you been doing any monitoring of that afterward?
Yeah. Well, we have the repeat Lidar flights, and there's some talk about using INSAR just to look at the whole corridor, yeah, we haven't. There's one thing that, with that toe being gone, that you would expect if something could happen, that would start. Right? We haven't really seen any movement there at all.
I guess just to build on a previous question, is there any history in this particular geological setting of rock-based landslides which dam the river?
No, not. We don't have any evidence of rock-based landslides. It's just that in the higher parts of the plateau, that's inset, we have something that look like bedrock spreads in basalt. And I don't know if those the ridges have a lot of rock in them, like these transverse ridges. I don't know what they're moving in, but it could be the material that's under the basalt that's carrying the movement. But
last question.
Yeah, not so much a geotechnical question, but I saw some interesting photospheres and point clouds on the ministry website during the event. I'm just curious what sort of other drone work was done leading up to the event.
Yeah, like there is the data portal on the government website, and that has kind of a fraction of the drone imagery that was out there. I think Spexy was doing like 2, 3, 4 flights a day. They're kind of doing laps out there, so I think there's definitely a phenomenal data set for someone to do some really good look on, the deformation of the slide as it was being filled. Like standing out there, you'd hear like a tree snap in the slide body every now and then from just like the stresses redistributing. So I'm sure there's something that'll show up there. And then I I think they did 4 or 5 flights while the breach was occurring too, so that like actual breach progression, there's a phenomenal amount of data there for someone to chew on.
Mostly photos and photogrammetry.
Yeah, the Spexy folks were set up with photogrammetry, and then the Lidar was there was the pre-slide, July or August 4th, August 8th, August 18th, and now March.
And that was all fixed in helicopter-based LiDAR.
Yeah.
Yeah. But I think for the Spexy stuff, they make surface models of all of their...
It was like a photogrammetry derived surface model, yeah.
Can I ask again?
Okay.
I'm sure Chilcotin First Nations are very interested and concerned about the river.
Mm-hmm.
You mentioned potential hotspots, flood rivers there. No doubt there will be ongoing adjustments in the channel and then stabilizing smaller events, smaller dams. But if a big one does occur where it's coarse rock and that won't move as easily as what we just had, which could potentially block fish.
Mm-hmm.
Are there thoughts about like planning for that scenario and what to do? Like we had in the Fraser a few years ago when the fish, and they were doing the magic fish.
We're actually involved in a project with the Chilcotin National Government right now looking at risk to fish passage, and which is a very different risk assessment kind of framework than I'm used to, like mostly focusing on human life safety, but now we're looking very much at the fish life safety, and where, like you say, anywhere where it's rock is a much higher risk of a persistent blockage forming, much like Big Bar back in 2019. So definitely it's work in progress. Maybe next year we can reprise.
Great. I'm going to cut the questions there. Brian is online, but Marten and Andrew are still in the room. You can ask some questions after. Before I say thanks to our speakers and turn you all loose, there is a talk next week on Thursday. I cannot remember what that talk is about, so look forward for that in your email and check your spam if you don't see it in your email box. The other one is that the symposium will be on June the 6th. Early bird tickets are still going, so please sign up, and it will be on deep foundations. So with that, I'm going to thank our speakers. Andrew, I'm a little bit of a deer knife to the heart on the flak one, but I'll forgive you for that. Thank you guys for making the talk very digestible to all of us. I don't have a background in geohazards, and it was quite interesting to see all of this. So thank you very much, and with that, I'm going to give the two of you bottles of wine. Brian, sorry you're online. You can't get yours in person, but I understand we're trying to hook you up with something. You can send it?
You can send a bottle of single malt instead.
They will hear that and try to accommodate your request. So with that, Andrew, I've been instructed that the Clos de Soleil is for you, and the Roche, which I love this, and I have this one sitting at home there, Marten, is for you.
Thank you very much.
So thank you very much, and great talk. All right, roll loose. Clean up the food in the back.
Thanks, Brian.
Thanks, everyone.
Yeah, bye, Brian.
Sorry I wasn't there. Okay. Enjoy.
Mohammed, I'm going to let you finish that up. How have you been?
Thank you very much.
Okay, thank you. Bye-bye.
Yeah, Marcus.